Hi guys, here we go. We are taking notes on 9-1, which is factors and greatest common factors. So we're going to start out here with just some definitions. The definition of a prime number is a whole number greater than 1 whose only factors are 1 in itself. So some examples of this, of what a prime number would be a number like 3, because the only factors of 3 are 1 and 3. 1 times 3 is the only thing that makes 3. 5, same thing. 1 times 5, the only thing that makes 5. 29, 1 times 29, nothing else can multiply to make 29, no other whole numbers. And like negative numbers are included in this too, so negative 13, negative 1 and 13, so 1 and negative 13. So those are prime numbers, a whole number greater than 1 whose only factors are 1 in itself. Now, composite numbers, on the other hand, are whole numbers greater than 1 that have more than 2 factors. So just the opposite of what a prime number is. Composite number has more than 2 factors. So some examples of this would be 4. Again, 4, besides 1 times 4, you could have 2 times 2. 2 times 2. The number 100, obviously 1 times 100, 2 times 50, 5 times 20, lots of different things multiply to make 100. And same thing with negatives, negative 136. Lots of different things can multiply to make negative 136. So those are examples of composite numbers. So now we're going to do some examples here. Just 2 examples, and all we want you to do is determine how to factor each of the following numbers and then classify them as prime and composite. Now, how to factor the numbers is kind of what I was just talking about earlier. You just list the things that will multiply to make the number at hand. So for number 24 here, let's get off of that. So for number, still got that. There we go. So for number 24 here, or for the number 24, I'm going to think about things that can multiply to make 24, like 1 times 24, or 2 times 12, or 3 times 8, or 4 times 6. So those are all things that multiply to make 24. So since there's obviously more than just 1 in itself, this number is composite. So then let's think about the number 31. Well, you might start thinking about 31, and obviously, everything's 1 times itself, so 1 times 31, and maybe use your calculator and check some other numbers like 3 and 4 and 6, things like that. You'll find that there are no other numbers that multiply to make 31 other than 1 and itself, so this number is obviously prime. Okay, so we're going to move on and do some more definitions. The next definition is prime factorization, and here you go. Definition of prime factorization is a whole number expressed as the product of factors that are all prime numbers. So copy that down, and then we'll explain that more here in a minute. But think about what that means. A whole number expressed as the product of factors that are all prime numbers. And then we're also going to mark out factored form. We're not going to talk about factored form in this section, just prime factorization. So let's move on to some examples then. All right, so here we're going to show you how to actually find the prime factorization of a number or a monomial, or monomials, because we know numbers are monomials. So this you may have seen before. This is where you're going to use factor trees. So let's look at example A here with 84. What you're going to do is you're going to break down 84 into two numbers that multiply to be 84. I always start on even numbers with small numbers, so I'm going to say 84 is 2 times 42. Now what I also recommend you do is when you're doing this factor tree, circle the prime numbers that you get. 2 is obviously a prime number, so I'm going to circle it. 42, however, is not a prime number, so I'm going to break it down, and maybe I use 2 again. So I say 2 times, what is that, 21? And again, 2 is a prime number. 21 is not, though, so I'm going to break 21 down. 21 breaks down into 3 times 7, and 3 and 7 are both prime numbers. You'll know that you're done when all of your branches have come to a stop. So 2, 2, 3, and 7 has stopped, so the prime factorization of 84 is 2 times 2 times 3 times 7. So think about what the definition said just a second ago. It said a whole number expressed as the product of factors that are all prime numbers. These are all prime numbers, and if I multiply 2 times 2 times 3 times 7, you will get 84. So that is the prime factorization of 84. Now, you may also shorthand this a little bit by using exponents. You could say 2 squared times 3 times 7, and that would be another way to express that same answer. All right, very good. So let's do negative 132. Negatives have one little trick to them, one little extra step, and that is that the very first branch needs to be negative 1 times the whole number, or I'm sorry, times the positive number, and then you count negative 1 in as your prime number. So negative 1 times positive 132, and now I'm going to break down 132. Again, it's an even number, so I know 2 is going to go into it, so I'm going to use 2 and 66. Again, 2 is a positive or a prime number, so I circle it. I'm then going to break down 66. Got a couple of choices here: 6 and 11, 3 and 22. Let's use 6 and 11. And in this case, the 11 is the prime number, so it gets circled. The 6 is not, because 6 can now break down into 2 times 3. And 2 and 3 are both prime numbers, so they circle. All of my branches have come to a stop. So the prime factorization for negative 132 is negative 1 times, there are 2 2's, so 2 squared times 3 times 11. Done. Okay, now next two examples is with a monomial that includes variables. But again, this is really just prime factorizing the number part of it and then carrying along the variable part. So for 18, we're going to break this down. 2 times 9. Circle my 2. 9 then is 3 times 3. Obviously those are both prime. So for this monomial, the answer is going to be 2 times 3 squared times x to the third times y to the third. Now, obviously you could write out, 2 times 3 times 3 times x times x times x times y times y times y. But again, the shorthand version is good enough. You don't need to write it all out like that. You can if you want. I'm not going to count it wrong, but I think 2 times 3 squared times x to the third times y to the third is the easier way to do that. All right, so last example here. Again, maybe try this on your own by pausing the video. If not, this is what it looks like. Negative 1 times 26. 26 then is 2 times 13, and those both are actually prime, so my answer here is -1 times 2 times 13 times r times s times t squared. Alright, so here in a minute you'll see how we're going to use prime factorization to actually help us with some problems, because again, this isn't necessarily something you're going to really do by itself very often, but we are going to use prime factorization here in a minute. I'll show you how. Okay, so a couple more definitions and then we're done here. This is kind of the key to the section, greatest common factor. That's what we're actually doing in this chapter, is doing things with greatest common factors. So first of all, the definition for the greatest common factor is the largest factor that two or more monomials share. Now this is actually nothing new. This is something you should have learned actually way back middle school, grade school even, is what the greatest common factor of two numbers are, like 12 and 18. We're just throwing monomials in there too, because now we know that monomials can be numbers, or 2xy is a monomial also. So the largest factor that two or more of them share. Relatively prime is when two or more monomials have a GCF of 1. The monomials themselves may not be prime numbers, but when you're looking for the greatest common factor of the two monomials, it's only 1. So that would mean that the two monomials are relatively prime to each other. So pause the video if you need to get that written down. We're going to move on to the examples. So for letter A here, we are simply trying to find the greatest common factor of 18. Now, again, greatest common factor means the largest factor that the two numbers share. So there's actually a couple ways you could go about this problem. Kind of the old way here, something we may have done in grade school, is just list out the factors of 12, meaning 1 times 12 makes 12, 2 times 6 makes 12, 3 times 4 makes 12, and I wrote those in ascending order, going from the smallest ones to the largest. So those are your factors of 12, 1, 2, 3, 4, 6, and 12. You could then do the same thing with 18. 1 and 18, 2 and 9, and then 3 and 6, and those are all your factors of 18. And then to get the GCF, or the greatest one of these, you just look and see what's the largest one they have in common. The largest one they have in common is 6, so the GCF is 6 for this problem, which is the correct answer. Now, problem with that method where you list out all the factors is, if you look at maybe the next problem, you have the number 180, or you might have the number 560. Well, listing out all the factors of 560 might take you a while. So this is where prime factorization comes in handy. What you can do is you can prime factorize each of these numbers. 12 would be 2 times 6, circle my 2. 6 is 2 times 3. So for 12, I would have 2 times 2 times 3. And I am going to write this out without using exponents, and you'll see why here in a second. 18 then, I write out as 2 times 9. 9 then is 3 times 3. So for 18, I write out 2 times 3 times 3. Now, the way you can use prime factorization then is you look at your prime factors here for 12 and 18, and you circle any that they have in common. So they have a 2 in common, and they have a 3 in common, and you write 2 times 3. You don't write the 2 twice. They have a single 2 in common, and they have a single 3 in common, and you multiply those two together to get 6, or your GCF. Now, the reason that'll save you time is you'll see in the next problem, it's going to be a lot less numbers to list out if you list out the prime factorization than it would be to list out all the actual factors of the number. All you got to remember then is to multiply the two prime factors together to get your answer, or the multiple prime factors together to get your answer. So let's do that with letter B. Let's break down 54. 54 breaks down into 2 times 27. Circle my 2. 27 is 3 times 9. Circle my 3. 9 is 3 times 3. So for 54, which I'll write over here somewhere, let's do it right here. For 54, I have 2 times 3 times 3 times 3. And again, I need to write it out without the exponents because I need to circle things that are in common. I'm going to do 63. I'm going to do my factor tree up in this case. 63 is 9 times 7. 7's prime. 9 then is 3 times 3. So for 63, I have 3 times 3 times 7. And then 180. And again, this is kind of the key here. 180 is so big, I don't want to list out all the factors of it, and it'd be hard to do. I'd do 1 and 180, 2 and what, 90, 3 and what, 4 and what, 5 and what, 6. So in this case, I can just do the prime factors. And I say, okay, well, this is going to be easy. 2 times 90. Now 90, again, you have choices. 2 times something, maybe I'll do 3 times 30. 30, maybe I'll do 3 times 10. 10, I do 2 times 5. So for 180, I have, and again, try to do smallest to largest, so 2 times 2, because there were 2 2's, and then 3 times 3, and then times 5. Now, again, I'm looking for what they have in common. They have, it looks like, let's just go right here. They have a single 3. Oh, let's back that up. I didn't take this guy's first one. So here's a 3 in common that they all have. So I'm going to write that 3 down. And then it looks like they have another 3 in common. They all have a second 3. And they do not all have 2's. They do not all have 7's or 5's. So it's just 3 times 3, which is 9, meaning the GCF for this problem is 9. Done. Okay, so let's look at some monomials that include variables, but again, it's going to work out the same way. For 36, I'm going to prime factorize it, so I'm going to say, let's do 2 and 12. Again, it's your choice. I'm going to do 2 and 12. 12, I'm going to do 3 and 4, and then 4 is 2 and 2. So for 12 here, and actually it's 12, or I'm sorry, not 12, it's 36 x squared y. I'm going to write my prime factors, which is 2 times 2 times 3 times 3, and then I also need to write out my variables, which will be 1x, 2 x's, and 1 y. And let's not get this problem moving over into the other problem. So there's my 36x squared y. So for 54, I'm going to break it down into, let's do 6 and 9. Neither of those two are prime, so I just break them both down. 6 is 2 and 3, which are both prime. 9 is 3 and 3, which are both prime. And again, all my branches stopped. So for the 54x y squared z, I have, what is that, 2 times 3 times 3 times 3, and then I have a single x, so 1x, excuse me, 2 y's, and a single z. And again, I'm going to go through the same process. I'm going to just circle what they have in common and write it down. They have a 2 in common. They have a 3 in common. They have another 3 in common. They have an x in common. They have a y in common. And that's it. So for this example, we have 2 times 3 times 3 times x times y, which is 18xy. So the GCF of those two monomials is 18xy. As you get better at this, you may be able to do this more quickly. You may not even have to use the prime factorization if you know that the largest number, 36 and 54, are divisible by is 18. Well, then you have your 18, and then if you can look and say, well, they have one x in common and one y in common, you know, you can get to that, but we'll get better at that as we go through this section. All right, last problem. Maybe go ahead and try this one on your own also by pausing the video. But as far as how it's done, we have 1 times 13. So that one's going to be an easy one. I'm going to go ahead and break down 91. Now this is one you'd probably have to use your calculator on because 91 looks prime, but it's not. It's 7 times 13. And again, the only way you might do that is typing in 91 and dividing it by some things. Is 91 divisible by 3? Is 91 divisible by 4? How about 6? How about 7? You take 91 divided by 7 and you're going to get 13. So 7 and 13 works for that problem, or for the 91. So I write out 13 ABC. The prime factorization of that will be 13. A times B times C. And then 91 x, y, z squared will be 7 times 13. And then times x times y times z. And we look to see what they have in common. Obviously they have this 13 in common, and that's it. They don't have any variables in common, so the GCF for those two monomials is just 13. And keep in mind, we didn't do an example like this, but if I would have had two of these, and like this last problem, if the only thing these two would have had in common would have been a 1, because they obviously all have 1s, if the only thing they had in common was a 1, you would have said that these two monomials are relatively prime. Relatively prime meaning their GCF is 1. You would say 1 and that they're relatively prime. So that's all we're doing for this section, and really again this section is just kind of a lead-in to the next sections. You really have to be able to find GCFs in order to do the rest of this chapter. GCF is kind of the key to this whole chapter. So, all right, go ahead and start on your homework.